Data science interview questions. What is data science? List the difference between supervised and unsupervised learning. Data science is an interdisciplinary field that combines statistical analysis, machine learning, and domain expertise to extract insights and knowledge from data. It involves using various techniques and algorithms to collect, process, analyze, and interpret large volumes of data to uncover patterns, make predictions, and solve complex problems. Difference between supervised and unsupervised learning. Supervised learning definition. Supervised learning is a machine learning approach where the model learns from labeled data, which means it is provided with input data along with corresponding target labels or outcomes. Objective. The objective of supervised learning is to build a model that can make predictions or classify new unseen data based on the patterns and relationships learned from labeled training data. Data requirements. Supervised learning requires a labeled data set where the input variables and their corresponding output values are known. Training process. In supervised learning, the model is trained using labeled examples and the algorithm learns to map the input variables to the desired output. Example of supervised learning algorithm include linear regression, logistic regression, decision trees, random forests, support vector machines, and neural networks. Unsupervised learning definition. In unsupervised learning is a machine learning approach where the model learns from unlabeled data, meaning there are no predefined target labels or outcomes. Objective. The objective of unsupervised learning is to discover patterns, structures, or relationships within the data without the need of predefined labels. It is used for exploratory data analysis and gaining insights into the data. Data requirement. Unsupervised learning can work with unlabeled data or data where only the input variables are available. Training process. In unsupervised learning, the model identifies inherent patterns, similarities, or clusters in data without any guidance from known labels or outcomes. Examples of unsupervised learning algorithms include clustering algorithms, for example, k-means, hierarchical clustering, dimensionality reduction techniques, principal component analysis (TSNE), and generative models, Gaussian mixture models. In summary, supervised learning deals with labeled data and focuses on making predictions or classifications based on provided labels, while unsupervised learning learns from the unlabeled data and aims to discover hidden patterns or structure within the data. Supervised learning versus unsupervised learning. Supervised learning, unsupervised learning. Input data is labeled, input data is unlabeled. Split in training validation test, no split. Used for prediction, used for analysis. Classification and regression. Classification and regression is part of supervised learning. Clustering, dimension reduction, and density estimation, that is part of unsupervised learning. What is selection bias? Selection bias refers to systematic error that occurs in statistical analysis when sample or data used for analysis is not representative of the population of interest. It occurs when certain individuals or groups are more likely to be included or excluded from the sample, leading to a distorted or biased result. Selection bias can occur in various ways, such as non-random sampling. When the sample is not randomly selected from population, it can lead to bias. For example, if a survey is conducted only among a specific age group, the result may not be generalizable to the entire population. Second, selection bias. Self-selection bias. This occurs when individuals or participants self-select to be part of a study or survey. It can lead to biased results if those who choose to participate have different characteristics or opinions compared to those who do not participate. It occurs when a subset of individual subjects are included in analysis, missing data lost to follow-up. This can lead to biased conclusions if the excluded individual different from different characteristics or outcomes. Pre-screening bias. When participants or subjects are selected based on certain criteria before the study or experiment, it can introduce bias. For example, if participants with certain pre-existing conditions are excluded from a clinical trial, the result may not be applicable to the broader population. Number 5. Publication bias. This occurs when the decision to publish or report research finding is influenced by the significance or direction of result. Studies with positive or statistically significant results are more likely to be published, while studies with non-significant or negative results may be unpublished or go unnoticed, leading to an incomplete representation of available evidence. Selection bias can significantly impact the validity and generalizability of research findings. It is important to carefully consider the methods used to select the sample or take steps to minimize bias, such as random sampling, stratified sampling, or appropriate statistical adjustments. Awareness of selection bias is crucial in ensuring the accuracy and reliability of statistical analysis and research studies. What is a bias variance trade-off? Bias variance trade-off is a fundamental concept in machine learning and statistical modeling that refer to relationship between bias and variance of a learning algorithm or model. Bias is an error introduced by the approximating a real-world problem with a simplified model. It represents the difference between expected prediction of model and the true value. A model with high bias tends to oversimplify the problem and make strong assumptions, leading to underfitting. It may overlook important patterns or relationships in the data, resulting in low accuracy and poor performance. Variance. The variance is the error introduced by models' sensitivity to fluctuations in training data. It measures the variability of models' predictions when trained on different subsets of data. A model with high variance is more flexible and complex, capable of capturing intricate patterns in training data. However, it may also pick up noise and random fluctuations, leading to overfitting. The model may perform well on training data but generalize poorly to unseen data. The bias variance trade-off arises from inherent tensions between bias and variance. A model that is too simple, high bias, will have low variance but high bias error. On the other hand, a highly complex model, low bias, can have low bias error but high variance. The goal is to find the right balance between the bias and variance to achieve optimal prediction performance. As models become more complex, they tend to have lower bias but higher variance. This is because they can capture more intricate patterns and relationships in the data, but are also more prone to overfitting. Conversely, simpler models have higher bias but lower variance. The trade-off involves finding the optimal levels of model complexity that minimizes the overall error. It often requires selecting the appropriate algorithm or model architecture, tuning hyperparameters, employing regularization techniques to control bias and variance. The bias-variance trade-off has important implications for model selection, evaluation, and generalization. It highlights the need to strike a balance between model complexity and generalization performance, ensuring that the model is both accurate on the training data and capable of making accurate prediction on unseen data. Low bias machine learning algorithms are decision tree, KNN, and SVM. These are low bias machine learning algorithms. High bias machine learning algorithms are linear regression and logistic regression. What is confusion matrix? A confusion matrix, also known as an error matrix, is a table that allows the visualization of performance of classification model. It is widely used in machine learning and statistics to evaluate the performance of a classification algorithm by comparing the predicted class labels with the actual class labels of dataset. Confusion matrix is typically represented as a square matrix where the rows correspond to the actual classes and the columns correspond to the predicted classes. The diagonal element of matrix represent the correct prediction, true positive and true negative, while the off diagonal elements represent the incorrect prediction, false positive and false negatives. So this is a matrix: actual positive, actual negative, predicted positive, predicted negative. So this is true positive, this is false positive, false negative, this is true negative. Classification of the confusion matrix consists of four cells. True positive, the number of instances that are correctly predicted as positive. True negative, the number of instances that are correctly predicted as negative. False positive, the number of instances that are incorrectly predicted as positive. Type 1 error, that is called type 1 error. False negative, the number of instances that are incorrectly predicted as negative, that is type 2 error. The confusion matrix provides valuable information about the performance of a classification model. From the matrix, various evaluation metrics can be derived, such as accuracy, precision, recall, F1 score, which help assess the model's predictive power, sensitivity, specificity, and overall performance. By examining the confusion matrix, one can gain insights into the types of errors made by the model, identify any class imbalances or biases in predictions, and make informed decisions about model strength and weaknesses. It is especially useful when dealing with imbalanced datasets or when different types of errors have different consequences in application domain. Basic measures derived from confusion matrix. So this is these are the formula.